Hi, greetings to Hungary. My name is Vlastimil Vojáček. I'm from the Astronomical Institute of the Czech Academy of Sciences, and I prepared a talk about the oxygen line in fireball spectra. Next slide. Okay, so the oxygen triplet at 777 nanometers is one of the most dominant lines we can observe in meteor spectra. And although the oxygen is present in some stony meteoritic material, the major source of the radiation is from the atmospheric oxygen. And it is known that this radiation is velocity dependent. Oxygen is bright in fast meteors, and sometimes it's undetectable in the slowest ones. And here you can see example of meteor spectrum, and here is the oxygen line. And yeah, so we decided to study this line to be able to calibrate the satellite observation of fireballs. The geostationary lightning mapper, or GLM, on board the GOES weather satellites can be used to observe fireballs. These detectors basically cover the Western Hemisphere or most of the North and South America. And they are designed to observe lightnings even during the day. And this is possible by using very narrow 1.1 nanometer narrow band at 777 nanometer. So the lightnings are short events and fireballs are longer, so they can be filtered out, and the time and position with the light curve of received energy is available for online and for public. And you can see one example of one fireball observed by GLM. So the question is how to calibrate the reported narrowband radiation at 777 nanometers to obtain the broad spectral brightness of the fireball, like the visual magnitude. Due to the velocity dependence of the oxygen radiation, this is not trivial. In the work of Janiskens and colleagues, they use GLM observations and compare them with the ground-based observations. And thanks to slow velocities of their sample of meteors, they assumed only blackbody radiation of 6,000 kelvins. That means that for the blackbody of this temperature, the radiation at 777 nanometers is simply about 1,000 of the overall radiation. And they were able to more or less sufficiently calibrate the GLM data. But for fast meteors, when the oxygen dominates in this region, the continuum assumption is not valid anymore. So we were wondering if it will be possible to derive some general velocity dependence of the radiation of oxygen and to be able to calibrate the GLM data for the whole velocity range of meteors. And for this, we used the newly developed spectral cameras that are part of the European Fireball network. And we collected, when we started selecting the meteors from more than 200 spectra, we selected 43 spectra with representative meteor velocities. And here you can see example of 3 meteors with different velocities. The slow one, the fast one, and meteor with somehow average or middle velocity. So you can see or you can't see the oxygen in the slow one, and you can see that oxygen in the fastest one is one of the brightest line for this spectrum. Our meteor network is not overlapping with the coverage of ghost satellites. So we compared the measured radiation of our sample in the oxygen region with the measured visual magnitudes of same fireballs, or with the broadband radiation. And we derived a simple calibration that can be applied for genome data. So here in the figure left, you can see the velocity dependence of the relative radiation in the oxygen radiation in the oxygen region to the broadband spectral radiation. And this fit allows us to obtain the parameters A and B in this equation. And now, if you know the velocity of the fireball and the radiation in the oxygen region, you are able to derive the broadband radiation. And you can see that for a slow meteors, the radiation in the oxygen region is about 1,000th of the overall radiation. But for fast meteors, it can be up to 1/10 of the overall radiation. So this is a big difference. And here on the figure on the right, there is velocity dependence of the sum of the visual magnitudes and the radiation in the oxygen region. And by fitting this, we derived the parameters C and D in this equation. And again, if you know the velocity of the fireball and the radiation in the oxygen region, you are able to estimate the visual magnitude. And this also implies that, okay, this also implies that the stated threshold magnitude for faintest fireballs that the GLM detectors can detect is about -14, but this is valid for slow meteors. And you can easily derive that for meteors with velocities about 70 kilometers per second, this threshold magnitude for GLM is about -8 magnitude. You can notice that in the velocity dependence of these values, some meteors are deviating, and we notice that the radiation of the oxygen also depends on the altitude. There is also slight dependence on brightness of meteors, and also during the flare, when a lot of meteoritic lines are radiating, the relative oxygen brightness compared to the observation outside the flare is lower. So we also derived the dependencies of the parameters from the equations before on these effects, and we were able to improve the magnitude estimate, or the difference between the magnitude estimate in the first correction to the observed visual magnitude from, in both cases, it was up to 2 magnitudes, and then we were able to have the difference within 1 magnitude. And we also, so when we apply this correction to the real GLM data, we also compared the observations of the same fireballs that were observed by GLM and by the US government sensors. And we had velocities for these because by USG is providing the velocities of observed fireballs. And here you can see our estimates in the colored points using our methods, and the gray ones are energies estimated assuming the black body radiation in the oxygen region. And you can see that these methods for slow meteors are more or less in an agreement, definitely within uncertainty of the GLM observations. And after the correction on the brightness, the energy estimates looked like this. And we also compared our method with the previous works that calibrated several GLM fireballs, and that were also and these fireballs were also observed from the ground. And I know these figures are kind of busy, but well, the red ones, the red light curves are always the first estimates of our method, and the yellow ones is the estimate after the brightness correction. And you can see that our method is again more or less in a good agreement with the previous works. So we confirmed the dependence of the oxygen radiation on the velocity, and we developed the methods to calibrate narrow band fireball observations. But the knowledge of the velocity and also the altitude is crucial, not only for our method, but when you want to calibrate the GLM observations. Unfortunately, the GLM detections or detectors are not able to provide these meteor properties, and other types of observations have to be used to receive the velocity and so on, to be able to calibrate the GLM observation with higher confidence. So the assumption that the bright fireballs are usually slow and that the radiation in the oxygen region is only from the blackbody continuum have to be used very carefully. So this work is currently after review in Astronomy and Astrophysics and will be published hopefully soon. So thank you for your attention.